this section is going to be, well, let's say a little bit lengthy. There's a lot of stuff in here, and I'll probably have to break it into 2 videos. It's so long. But let's start with the following recollection, if you will. So let's recall that a set of vectors let's call them V1, V2, up to V sub P is linearly independent if, so it's linearly independent if whenever there are scalars, let's say C1, C2, up to C sub P. So if whenever there are scalars C1 such that C1 V1 plus C2 V2 up to CP VP equals 0. So whenever we have this situation happen, it automatically implies that C1 equals C2 equals dot dot dot. So all the C's are equal to 0. So that's what it means for a set to be linearly independent. Now, let's go ahead and start with it. Well, let me get a definition out of the way before I continue on. Let H be a subspace of a vector space B. A set of vectors, we'll call them B, B1, these are vectors, B2, up to BP is a basis for H if we've got 2 things that it needs to happen here. 1, B is linearly independent, and 2, H is equal to the span of those vectors. Let me do some examples to get you comfortable with this. So we need the vectors. Those are the 2 items that we need. Linear independence, and spanning. Those are the 2 things we need to be a basis. So let's take a look at some examples here. In R, let's start with R2. The vectors (1, 0) and 0, 1 are a basis for R squared. I think to see that they're linearly independent, all you have to do is form the matrix with these as columns. And you can see there are 2 pivot columns. The determinant's not equal to 0, whatever way you want to look at it. we know just from this, since there are two pivot columns tell us that the matrix is invertible. So as a matter of fact, we don't just have one, we also have two. Span, it does span because of that. So both of these things are all because we have two pivot columns, or the matrix is invertible, whatever way you want to look at it. You can even, if you want to, look, take its determinant. The determinant is 1 minus it. The determinant is non-zero, so there's another way we could have done it. In a similar fashion, 1, 0, 0, 0, 1, 0, 0, 0, 1 is a basis for R3. In fact, in these two examples, let me maybe do it here. E1, they actually have names. These vectors are so important. These three vectors are called the standard basis vectors for R3. And while I'm here, these two vectors up here are the standard basis vectors for R2. And it doesn't take much to imagine what would happen for R3, or for Rn, where n is unknown. We have E1 equals, you have 1, 0, dot, dot, dot. So 1 with all zeros. E2 equals 0, 1, 0, dot, 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 0. So there's a 1 and only its second component. You could look at like E sub k. That's where you'll have zeros up to a spot, and then zeros all the rest of the way. So that spot right there is the kth component. All the way until you get to E sub n. You'll need n of these vectors to do the job. Here's where we have 0, dot, 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 0, and then it finally ends with a 1. So these are the standard basis vectors for Rn. And you can see, if you want to see if they, clearly you should imagine that they span fairly easily, because well, you can see, well, let me do a real quick example to show that the spanning is so easy. Let me go back to R3. Here we have E1 was 1, 0, 0, E2 0, 1, 0, and then E3 is 0, 0, 1. Now, linear independence is easy. Put these three together to make yourself a matrix, and you can see immediately that, well, you have a diagonal matrix, it's invertible. You You have 3 pivot columns, therefore it's invertible, whatever you want to do. It also shows it spans, by the way, but I want to show you an easier way that it spans. If you have, say, an x, y, z in R3, then it's a linear combination of these vectors because x, y, z will equal x times 1, 0, 0 plus y times 0, 1, 0 plus z times 0, 0, 1. So this implies that E1, E2, E3 span R3. And in fact, let me draw a picture of these 3 things. If you haven't taken Calc 3 or a physics class, then you may not have seen this before, but this is a way to draw a 3-dimensional coordinate system in, this is a representation of R3. And so what we have here, we put a 1 here, a 1 here, and a 1 here. Let me darken this up a little bit because I want you to see it as a vector. That vector there is E1. This is the vector that goes from the origin to the coordinate 1, 0, 0. And it doesn't take much imagination here either. Let me make this a little thicker. That vector there is E2. And then finally we got a vector in the vertical direction. And that vector in there is E3. And so this shouldn't be minimized because this kind of mathematics was the impetus for all of linear algebra anyways. Physics had a lot to do with the development of calculus and, well, linear algebra. Linear algebra was invented after the fact to try to give mathematical theory to the whole process of dealing with vectors and solutions of systems of equations. Let's work some examples and see if we get some bases with given sets. So let's determine if, let's call it C. This will be the vectors 1, 2, comma, 3, 4, is a basis for R2. Well, 1, we need to show linear independence. Well, I should write linear. That means if I were to have, say, a number times the first vector plus a number times the second vector, if that linear combination equals the 0 vector, I want to show that A equals B equals 0. So let's see if that's actually the case. Well, what we can do here is rewrite this as a matrix problem. Well, there's a number of ways. I could take this matrix here and row reduce it, or I guess I could wait till I was in what do you call this? An augmented form. 1, 2, 3, 4, 0, 0. And I could do something like negative 2R1 plus R2. Then you'll see 1, 0, 3, negative 2, and the other side is still zeros, and that's good enough. Because you see now that you have two pivot columns. Column 1 is pivot column and column 2 is a pivot column. I could zero out that stuff up above there if I really wanted to to echelonize this even more, but I'm perfectly fine with this. This, by the way, also shows that they do span because, well, the same thing would happen if I had any kind of vector on the other side. Let me show you what I'm talking about. So let me first write this up. Two pivot columns. Mean the matrix is invertible. So therefore, C is linearly independent. Now what about spanning? Well, so for this, let x, which equals xy, be any vector in R2. Can we find a vector, or let's call it, I don't know, A, which equals to AB? Can we find a vector such that what were these vectors again? 1, 2, 3, 4. 1, 2, 3, 4 times AB equals that given vector. Well, I've already answered the question in the first part. Since this matrix here is invertible, I can in fact find these. AB as a vector will equal 1, 2, 3, 4 inverse times xy. And so you will have solutions for AB. This implies that C spans R2. So C is a basis for R2. Let's try one for R3. Example. Determine if C, which equals 1, 2, negative 3, comma, negative 4, negative 5, 6 is a basis for R3. Well, let's try again. Let's see here. We have linear independence. Let's try that. Linear independence. So with linear independence, once again, let's take a look at the matrix formed by using these vectors as columns. Okay, so here I can't really take a determinant and figure out if it's invertible, which would tell you it's probably not going to span at the very least, but they still may be linearly independent. So what I'm going to do is perform elementary row operations. So I'm going to take negative 2 times the first row and add it to the second row. So I'll have, well, the purpose of multiplying by negative 2 was to wipe out this particular entry. And then, let's see, Negative 2 times negative 4 makes that 8. So there's a 3. And then I want to take out the third row if I can, or at least this first item. So I'll do 3r1 plus r3. Let's see, negative 12 plus 6 gives me negative 6. Just to complete the process, I'm going to take twice row 2 and add it to row 3. You don't have to go any farther than this. I can see we have 2 pivot columns. Here's my pivot here, my first pivot for column 1, and there's my pivot for column 2. So 2 pivot columns implies linear independence. Now what about spanning? So in this case, we're going to let this time x equal x, y, z be in R3. Can we find scalars A, B, and C in R such that where are my 3 vectors? Oh, 1, 2, negative 3, such that A times 1, 2, negative 3 plus B times negative 4, negative 5, and 6 is equal to x, y, z. Just got a little carried away. I did not need a C vector or a C scalar at all. I would just need 2 scalars for 2 vectors. Well, convert this to matrix notation as usual. Or let me just go augmented here. And let's perform elementary row operations until it's clear one way or another if I'm going to have a solution for any x, y, z you can imagine, or if not. So let's see what happens when we start row reducing. Exactly the same things as I did before are going to happen again here. So I'm going to take negative 2 times the first row plus the second row, and I'll take 3 times the first row plus the third row. So, well, the first row, of course, will stay the same through all of this. The second row, which was the one I was actually targeting these numbers here, this 2 and this negative 3. Let's go ahead and put my zeros down there because they were targeted, so they're taken care of. Now, I did negative 2 times the first row plus the second row. So negative 2 times negative 4 is 8. Minus 5 gives us a 3. And then negative 12 plus 6 gives us negative 6. Now, the other side, I don't have zeros this time, so I got to be careful. Negative 2 times this plus negative 2 times the first row, negative 2x plus y. And then for the third row, it looks like I'm going to have 3x plus z. Then what I'm going to do is I'm going to wipe out this negative 6 by taking twice the second row and adding it to the third row. So 2r2 plus r3. The first row is unaffected. The second row is unaffected. For the third row, we'll zero out those. And in the last column here, I have to take twice this, so negative 4x plus 2y plus 3x plus z. It looks like negative 4x plus 3x will be negative x. Then I'll have 2y plus no y will be plus 2y. And then I have, well, z plus z. So let me just make sure of that. 2 times this would be negative 4x plus 2y. And adding to that, negative x plus 2y. Now, this would be good if this vector turned out to be 0 no matter what x, y, and z were. It will not be good if I can just come up with numbers, any numbers I want, to make this not equal 0, then I will know this thing does not span. So let's find, well, this won't be hard to do. Let's just pick some numbers here. I could do, I don't know, let's try x is equal to 0, y equal to 1, and z equal to 0. So negative x plus 2y plus z will equal 2, which is not equal to 0. So this has no solution. So that set C does not span. R3. So C is not a basis. For this last example, see if you can invent your own vector that does not work here. All you got to do is come up, like I said, come up with any combo of x, y, and z that don't equal 0, that force this row to be false, and you'll have it. The standard basis for P sub n is 1 comma t squared, t cubed, dot, 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 all the way until you get to t to the nth power. You should be able to see that it spans. Linear independence is very simple, but let's take a look at spanning. Well, let's do linear independence. Here we have, can we find, let's see if we have A1 up to, actually A sub 0 up to A sub n. Let those be real numbers. But we have A0 times 1 plus A1 times t, plus A2 times t squared plus A sub n t to the n. Suppose that were equal to 0. Now remember, this is a little bit different here because this has to be true for all possible values that we might plug in for t. If there's any value for t in which this zeroes out, then well, I don't know if we'd want to say it that way, but this I have to find these that equal 0 no matter what values of t we're going to be using. So check this out. If you let t equal to 0, all I'll end up with is a sub 0 equals 0. Well, there I have the first coefficient down. Now for the rest of them, so here's what I have left then. I have a1t plus a2t squared plus a sub n t to the n. And by zero, I'm talking about the zero polynomial. Well, you can play the same sort of a game. Well, I can't, if I plug in t equal to 0, this will just wipe everything out and I won't find out anything about a or not. What we could do is let me factor a t out. I think that's an n minus 1. So we can divide by t as long as t is not equal to 0. Then this is something that always bothered me in calculus. Now let t equal 0. Wasn't 0 before, but now when t equals 0, we get a1 equals 0. So we have a2t squared plus up to an t to the n is equal to 0. And as you can imagine, I'm going to factor out t squared this time and continue this game. You might remember a game similar to this when you were doing partial fractions, I believe. So I can divide by t squared. T is not equal to 0, but then I can plug in t equal to 0 after that. Now, another way you could do it, which is very interesting as well, you can still get this a0 equals 0, just like I did before. But now what you could do is take the derivative of this stuff. So you'll get an a1 all by itself, but then you'll have 2a2 plus 3a3 squared, 3a3t squared, etc. will equal to 0. And then you can allow t to equal 0 in the derivative and get this same process to happen. So anyways, by the time you're done, you will eventually get down to an equals 0. And so then we would have a0 would equal a1 all the way up to an is equal to 0. And so we have b is linearly independent. Does it span? I think it's very clear that it does. Let p sub t equal a naught plus a1t plus a2t squared plus dot 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 plus an t to the n be any polynomial in p sub n. Well, all you have to do then is, well, your scalars are right there. Let them be exactly these scalars. And, well, there you have it. This equals a naught times 1 plus a1 times t plus dot 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 plus a sub n times t to the n. So the vectors 1, t, all the way up to t to the n do in fact span. So b spans Pn. So therefore, b is a basis for p sub n. Is b equal to 1 plus t, 1 minus t, 1 minus t squared, a basis for P2. Well, let's take a look at first linear independence. I thought I would throw in another thing uh, before we get to it, but let me suppose I have a1 times the first vector plus a2, these are scalars, times the second vector plus a3 times the third vector. Does that equal 0? What will a1, a2, and a3 be? Well, let me distribute these through and then collect like terms. So I'll have an a1 plus a2 plus a3. That's the constant part. That will have to equal 0. Then the stuff that's attached to t, I have an a1 times t and an a2 times negative t. So that'll be a1 minus a2 times t will equal 0. And then finally, we have negative a3t squared equals 0. As usual, you can let t be anything practically that you want. For example, if I let t equal the number 1, when t equals 1, we immediately get a3 is equal to 0. That automatically changes this stuff up here. By the way, when t is equal to 1, we automatically get a1 minus a2 is equal to 0 as well. So I'll have a1 plus a2 equals 0. Then a1 minus a2 is equal to 0. Add them together. You get 2a1 equals 0. So a1 equals 0. And then from this equation right here, we'll see that a2 is equal to 0. So we have linear independence. Was it called B? Let me check. Yes. Linearly independent. Now, do they span? So, given any polynomial, let's say equals a naught plus a1t plus a2t squared, can we find constants or scalars see what letter should I use? Maybe B, I don't know. I'll stay away from B2. We'll call them C1, C2, and C3 with C1 times 1 plus t plus C2 times 1 minus t plus C3 times 1 minus t squared. Will that equal the given vector a naught plus a1t plus a2t squared? One of the things, I didn't quite do it up top, but I think now is a good time to do it. I'm going to multiply this out and collect like terms, but I want to show you something. If I multiply the constants, I'll get C1 plus C2 plus C3 equals 0. And then the terms for t, I had them as before, C1 minus C2 times t equals 0. And then finally, negative C3t squared equals 0. Now, I know from what we did before how we can determine each of these is or is not equal to 0, but let me show you something else. If I take this and multiply it all out and just leave it in one row, here's what I would have. I would have C1 plus C2 plus C3 plus C1 minus C2 t minus C3 t squared, and that's supposed to equal a naught plus a1 t plus a2 t squared. Now what you can do I see I made a mistake up here. The constant stuff is supposed to equal A1. The stuff that is in front of T is supposed to equal A1 T. Actually, that's A0. And the third one should be A2 T squared. Another way I could have done that is the following. If you look right here, this constant stuff should match the constant here. And this part right here should be the same as in front of T over here. So it's what you call matching coefficients. This coefficient should match the coefficient of the same power of T. Just like this coefficient here should match A2. Negative C3 should match A2. But anyways, let's go ahead. These are the equations that I have. I'm going to use this to further refine my equation. C1 plus C2 plus C3 equals A sub 0. C1 minus C2 equals A sub 1. And then negative C3 equals A sub 2. Well, that makes C3 easy. C3 equals negative A sub 2. Let me throw it up into the first equation and read my first two equations. I'll have C1 plus C2 minus A2 will equal A sub 0. C1 minus C2 will equal A sub 1. I'll go ahead and add this A2 to the other side. So I'll get C1 plus C2 equals A sub 0 plus A2. C1 minus C2 will equal A1. Now I'll do exactly like I did before. I'm just going to add these two things together. And I'll get 2C1 equals A0 plus A1 plus A2. So C1 will equal all that stuff divided by 2. And that gives me, what do I have? I have C3, I have C1. Now I need to go and get C2. Well, I'll use this equation right here to get me, maybe I'll use this first one to get me a C2. So what I'll do right there, I'm going to subtract the C1 from both sides of that equation. So C1 plus C2 was equal to A0 plus A2. Let me subtract C1. Of course, C1 we already had. And I really don't care about simplifying. All I care about is the fact that given an arbitrary vector in the vector space, I was able to find scalars. I was able to find scalars A or C1, C2, and C3 such that this would work out. That didn't matter what this was. I would be able to figure out C's for all of them. Now here comes something very big. It's a very, very, very big thing that I want you to really carefully pay attention to. I'm going to redo that last example. So redo the last example. Okay, and we were looking at B, 1 plus T, 1 minus T, 1 minus T squared. We were looking at that. Was that a basis? So does it span and is it linear independent? Well, what we can do is this. I want you to think about this. 1 plus T is the same as 1 plus T plus 0T squared. So what I'm doing is writing it so I have all the three components. Similarly, 1 minus t equals 1 minus t plus 0t squared. And then 1 minus t squared will equal 1 plus 0t minus 1t squared. So here's the way I want you to think about it. 1 plus t, I'm going to think of as this vector. 1, 1, 0. Look. 1, 1. Yeah, let me put ones in front of these too, so it's very clear. 1, 1, 0. These, like I told you before, these are like components. First component, second component, and third component. I'm going to do the same thing with this second vector. 1, negative 1, 0. And this third one, 1, 0, negative 1. If you did yours upside down of mine, suppose you always start from the highest power going down, no problems. You'll get the same, it will work. It'll just be upside down of what I'm doing. So, I guess I was going to do, yeah, let me do that then. 1 minus t will be that guy, and then 1 minus t squared is that guy. So this, let me snake it up over here so we can see which ones are which. Now I'm going to do the matrix stuff on this and see if I get an invertible matrix. So what I'm going to do is I'm going to wipe out this coordinate here by taking negative r1 plus r2. So when I do that, the first row is fine, but the second row I'll get 0, negative 1 minus 1 will be negative 2, negative 1 plus 0 will be negative 1. The last, I didn't do anything with the third row. And now you can stop. We have 3 pivot columns, or if you want, the determinant is non-zero. The determinant of an upper diagonal matrix is just the product of the entries on the diagonal. Since the determinant, I guess I'll pick this one, of 1, 0, 0, 1, negative 2, 0, 1, negative 1, negative 1, does not equal 0, the matrix is invertible. Well, that's beautiful, because now that means that it is not only linearly independent, the vectors are not only linearly independent, the columns here that are the vectors, they also span. So, therefore, the columns are linearly independent and they span. So B is a basis. So the matrix, the ability to do this is very powerful. It takes this problem. Look how quick we were able to determine all that. And you look at the previous example, nothing was very hard about the previous example, but just look at how time consuming it was to go through all of that. It started way up there, but then when I was able to use the power of matrices, boom, half a page at the most. Only reason why it's more of a half page is because I'm putting a synopsis at the end of each of these things.